Welcome. In this lecture, we're going to discuss one of the most fascinating ideas from complex systems, emergence. Emergence refers to the spontaneous creation of order and functionality from the bottom up. If we look at the physical world, we see emergent patterns at every level. There's spiral-shaped galaxies, our own solar system with the planets orbiting the sun, and even the giant red spot on Jupiter, which is really a storm that's been raging for at least 350 years. And it's more than 3 times the size of the Earth. All of these we can think of as emergent phenomena. And if we come back down to Earth, on our own planet, we see emergent structures everywhere. Mountains and rivers take wondrous shapes. Animals and plants exhibit beautiful patterns. If we take out a microscope to look even deeper, we see structure upon structure. Inside our human bodies, we see respiratory systems, nervous systems, skeletal systems. Each of these systems is comprised of small, differentiated, and structured cells that interact in such a way that they create something emergent that's more than the sum of its parts. So in sum, we see all this emergent structure all about us, and we see it at every scale. It's true whether we pull out a telescope to look far into space, or if we lean over a microscope to see inside, to see what things are made of. Now, not only do we see structure, but what's important is that these structures have functionality. Hearts beat, antelope run, rivers carry water to the sea, and so on. But here's what's amazing. All of this happens without a central planner. None of it's orchestrated from the top down, but it emerges from the bottom up. Exploring how structure and functionality emerge from the bottom up is perhaps the most profound and interesting question in all of science. So it should come as no surprise that this question animates scientists from a variety of fields. Right? It's a huge question in physics, chemistry, and biology. But it's also fundamental to the study of psychology, sociology, politics, and economics. After all, how does something like culture emerge? What makes for an effective city? How do we prevent the emergence of a Great Depression? These are all social questions that have at their core issues related to emergence. So in this lecture, we're going to learn a little bit about what complex systems has to say about emergence. We'll see through some examples how patterns and structures actually do emerge. And we're going to see how functionality emerges. Now, before getting into some deep scientific details, I want to describe a particular emergent phenomena. And I'm going to do this in order to drive home what emergence is. And I also want to sort of establish a feeling just of wonder and awe about how amazing this property is. I'm going to do this by talking about something that's actually a little bit gross. Slime molds. What are they? Slime molds are amoeba-like single-cell organisms. They feed on decaying plant and vegetable matter. So you might find them in these like reddish-orange blobs that you see on rotting wood in forest. Or if you live in the suburbs, they're that stuff that sort of discolors your bark, your mulch. Slime molds lead a pretty simple life. What they do is they absorb microorganisms, they secrete a little waste, and then they just sort of move on about their day. They don't write plays or watch television, they don't ride bikes or anything like that. Slime molds are interesting, though, because when under stress, and by stress here I mean just a lack of a food source, when they're stressed, they've got nothing to eat, what an individual slime mold will do is it'll secrete an enzyme. So you can think of this as a warning signal. Nearby slime molds will sense this enzyme, and if they're in similar straits, they'll sort of move in the direction of the other slime mold. And when they do, they'll secrete this enzyme as well. This creates sort of an even stronger enzyme path. So you can think of this as a party that's spreading by word of mouth, except for the fact that slime molds don't have mouths. What they're doing is secreting. So it's a party spreading by secretion, if you will. Now, it's not hard to figure out what's going to happen. As all these little creatures start heading toward some source that's releasing the enzyme, they're releasing more of it, you're going to get a colony that begins to form. So this colony looks sort of like Jell-O, like a globule of Jell-O. And like Jell-O, the colony consists of identical cells. There's no cell differentiation. Each slime mold is the same. So the colony has no heart, no brain, and like the lion, it has no courage. It's just 100,000 or so little creatures banding together to form a bigger creature. And this bigger creature has a name. It's called a pseudoplasmodium. Okay, here's where the story gets really interesting. The pseudoplasmodium can walk. The individual cells can move, but the pseudoplasmodium moves along like a slug. I mean, this is incredible, right? This is emergence writ large. You've got this functionality. What started out as a bunch of single, identical creatures is now a superorganism that sort of walks along. In fact, Early scientists thought of these pseudoplasmodia as creatures. They thought they were slugs, but they're not. They're just colonies of individual identical cells. But it gets even better than this. So at some point, so as we've got this little society of amoebas, this colony, it stops moving if it can't find food. And the individual cells, the individual slime molds start crawling on top of one another and create a stalk. Almost, think of this like circus performers that, create some giant human pyramid. Now, some of these creatures who are lucky enough are going to make it to the top of this stalk. And when they do, in a last-ditch effort to survive, they're going to produce some little spores. These are just seeds that spawn other slime molds. These spores are just spread by the wind or the rain. And actually, if you want, you can go on YouTube or some video on science show and watch videos of this. So these things started out as identical, but now they start forming different roles. Some form the stalk, and some create the spores. This is known as breaking symmetry. What started out as symmetric is no longer symmetric. This idea of breaking symmetry is going to be a core concept when we talk about emergence. So this is really, the slime mold is an epic emergent, right? We've got individual parts that are identical, produce something in the aggregate that's, for lack of a better word, just amazing, right? And they do this as a way to survive. Now, in some ways, it's difficult not to be awestruck by the example of the slime molds. But really, if you think about it, slime molds are nothing compared to the human brain. The brain consists of billions of neurons that are constantly reconnecting and disconnecting. They communicate through chemical and electrical pathways. And as a result, the brain is capable of many of the same tricks as your basic laptop computer. It can store data, it can recall things, and so on. But even more incredibly, it produces consciousness. Consciousness is, in many respects, the ultimate emergence. It's a functionality that exists at the macro level, the level of the brain, that cannot exist in the parts. A single neuron cannot be conscious, nor can a single neuron produce meaningful cognition, or can it experience emotion, right? Yet a collection of neurons can write this lecture and hopefully allow other people to make sense of it. Okay? So let's move on to the science of emergence. In the early days, when complex systems was just getting started, in the 1980s, the concept of emergence was characterized by sort of a duck test. If something cool happens at a higher level, it's emergence. So if it looks like a duck, it's a duck. Well, this is ocular science, right? Eyeball science. And we need to improve upon that. We need some sort of formal definitions and categorization. So in this lecture, we're going to talk through some real definitions of what emergence is and talk about types of emergence, and we'll see how it occurs. Okay, before we continue, let me remind you that the concept of emergence really lies at the core of complex systems. Again, by definition, complex systems consist of interacting parts, interdependent parts. They're diverse. But what fascinates scientists about complex systems is their ability, and maybe in some sense even their tendency, to create something new that's essential and unpredictable at a higher level, such as we saw in the slime mold or such as we see in the brain. Okay, so let's get on to these definitions. We're going to do this by talking about classes of emergence. I'm going to make two different distinctions between types of emergence. The first is going to be between simple and complex emergence. The second is going to be between strong and weak emergence. Okay, first, simple emergence. This is a macro level property in an equilibrium system, like the volume of a gas, the weight of a table, the strength of a piece of steel, or the wetness of water. This may seem less exciting than the slime mold, and it is, but it may be more profound, right? Remember, a single water molecule cannot be wet. The wetness emerges from what are relatively weak hydrogen bonds. It is for this very reason that the physicist Philip Anderson, in introducing the idea of emergence to the broader scientific community, coined the phrase, more is different. Simple emergence applies to systems in equilibrium. The slime mold was dynamic. So we refer to that as an example of complex emergence. Complex emergence is a macro-level property that exists in complex systems not in equilibrium, such as our mobile pseudoplasmodium slime mold, or such as a flame. So now we're going to get to the point of a controversy, a current controversy. Everyone, well, almost everyone, accepts that some macro-level phenomena, like consciousness, are emergent. The controversy stems from whether or not we can or ever will understand all emergent phenomena. There's some people out there who believe that there's some macro-level properties, like consciousness, that we're never going to be able to understand. And they call these strong emergent phenomena. So strong emergence says that what occurs at the macro level cannot be deduced from the interactions at the micro level. In contrast, weak emergence says that what occurs at the macro level cannot be expected from the interactions at the micro level, but we can explain it. So the slime mold is an example of weak emergence. No way would we expect the single-cell organisms to form a slug when times get tough, and then form a flower in order to reproduce. But once we see it, we can understand how it happens. We even know, or we think we know, that those that get to be the spores, those that actually get to send out the little pods, have their descendants populate future slime modes. So these are in some sense the winners. They're not in any way stronger, smarter, faster, or better looking than the other ones. They're just in the right place at the right time. Okay, emergence exists. That's great. But how does it exist? How does it arise? That's it. That's the real puzzle. That's something that a lot of us puzzle over a great deal of time when we sit around and think about complex systems. To see how emergence arises, I want to consider a model borrowed from Stephen Wolfram's book, A New Kind of Science. This model is known as a one-dimensional cellular automata. We're going to construct a small-scale version. Imagine I've got 3 light bulbs arranged in a triangle. So I've got one at the top, one on each side. Each light bulb can be in one of 2 states. It can be on or off. And we're going to assume that each light bulb uses the following rule. If all 3 light bulbs are in the same state, if they're all on or all off, they're all going to switch their state. Now, if none of the other light bulbs is in the same state as you, you switch your state. So if you're on and the other 2 are off, you're going to switch. But if one of the other 2 light bulbs is in the same state as you, and the other one's in a different state, then you're going to stay put. Okay? Those are the 3 rules. So let's suppose we start with 2 bulbs on and 1 bulb off. The 2 that are on are each going to have 1 other bulb in the same state. So they're going to stay on. But the bulb that's off sees no other light bulbs in the same state. So it's going to switch on. So therefore, after the first period, we're going to have all 3 light bulbs on. Now, once we've got all 3 on, they're all in the same state, so they all switch off, right? But then, since they're all off, they all go on. So what we get is a blinking set of lights. So in the more formal language of dynamical systems, this is called coupled oscillation. Now note that no matter how we initialize the 3 lights, we're going to get this blinking. If we start out with all 3 in the same state, then the blinking is going to start right away. Well, the other possibility is we have one of the lights in a different state than the others. But this is what we just did. This is what we just saw. And what happens is the lights take exactly 1 period, then they all get to the same state, and then they start to blink. So blinking here is an emergent phenomena. It wasn't built in, right? It just sort of emerged from the bottom up. Now, this sort of blinking occurs not only in strands of holiday lights, it also occurs in the biological world with fireflies. Fireflies are the biological world's analog to blinking light bulbs. Now, adjacent to my house where I live in Ann Arbor is this beautiful 30-acre prairie called Dow Prairie. Now, in warm summer evenings, you can walk through this prairie and you can see fireflies blinking in the tall grasses and way up in the treetops. It's just beautiful. The fireflies are so slow you can grab them in your hand, right, and catch them. Now, what's interesting about these fireflies is the flickering is just completely random. It's just like little flash bulbs going off, constantly, randomly. And at any instant, some of them are on, some of them are off. Now, suppose I were to move to the Philippines or to New Guinea or to a place called Elkmont, Tennessee. If I went to a prairie there, it would look very different, and here's how. In those places, the fireflies would all be blinking in unison. It would be like one giant stand of holiday lights blinking on and off as one. Now, how does this happen? This happens by a process very similar to the one I just described with the blinking lights. What's happening is this coordination emerges from the bottom up. There's no conductor, nor is there some sort of pendulum that provides a central signal telling the fireflies when to light up and when to dim down. Complex systems scholars have thought through this and uncovered the mechanism that produces this emergent blinking. How does it work? Here's a simplified version of how the synchronization occurs. Think of each firefly as having a little clock inside it with a spinning hand that makes a revolution every 10 seconds. So when this hand reaches the top of the clock, it triggers a mechanism so the firefly blinks. Now let's start with a whole bunch of fireflies. What they're going to do is they're all going to blink at random times. And they're going to look just like the fireflies in the prairie by my house. That's it. End of story. No synchronization. Blinking fireflies adjust their clocks to match their neighbors. So if a neighboring firefly flashes, then a firefly's clock will leap ahead to try and catch up. Now, why they do this is unknown. Some biologists speculate that the males are trying to flash first, and that those that flash first are preferred by females. So the syncing really isn't occurring in some sort of arms race. They're attempting to be first. Now, for our lecture, we're less concerned with why the synchronization occurs than in how it occurs. So in a formal mathematical model, what we could say is the firefly is matching the phase of its cycle to that of its neighbor. Now, if all the fireflies locally, this is all local, adjust to try and catch up to their neighbors, then what's going to happen is the entire population is going to get in sync. Now, this all happens locally. That's why emergent phenomena are called bottom-up. If there were a central conductor standing in the middle of the prairie waving a baton, then we'd say the blinking is enforced from the top down. Now, people do the same thing, just like the fireflies. We adjust our phase and our frequency. This is how if you see crowds at athletic stadiums performing the wave or producing rhythmic clapping, what they're doing is the same thing as the fireflies. They're getting their cycles in sync. Okay, I want to move away now from the blinking of fireflies to talk about the formation of culture. Now, these two are going to seem rather far removed, but we're going to see some similarities. In each case, what we're going to see is we're going to see coordinated behavior at the macro level that arises through micro-level interdependencies. Now, culture is a very difficult thing to talk about. It's tricky. It's got literally hundreds of definitions. So for our purposes, we're going to take a very constrained definition. We're going to say culture is a shared set of beliefs, behaviors, and routines. This includes important parts of culture, such as religious and artistic expression, and it does so in a very sort of abstract way. So what I want to do is I want to think that there's, let's say, 100 domains in which actions and beliefs are interdependent. Remember, that's a core part of complex systems, interdependencies. Well, when two people meet, their actions are interdependent. That's also true when one person locates or captures a resource. They can either sort of share it or hoard it. That's an interdependency. When I give lectures about cultural diversity, I often talk about where people store their ketchup, because where you store your ketchup depends on where other people in your family store their ketchup. So you've got, again, an interdependency. Now, a domain of belief is different from a domain of action. A domain of belief would be something like the answer to the question, why does the sun come up? One belief system could be that the sun is pulled across the sky by a chariot driven by a sun god. Another belief system could be that the Earth is spinning on an axis, so that it only appears that the sun is coming up. Well, there's all sorts of different belief systems that people could have, and there's all sorts of different sort of action domains that could exist. And what we want to do is let's just make a list and say there's 100 of these domains, and we'll write down sort of how each person behaves and thinks in each one of these domains. Now, on each of these domains, we're going to play a game that game theorists call a pure coordination game. We've talked about this before. What matters in this game is that people do the same thing. If we both do the same thing, we get a positive payoff. If we don't do the same thing, we get no payoff or a negative payoff. The classic coordination game involves choosing which side of the road to drive on. If everyone drives on the left, great. If everyone drives on the right, also great. But some people drive on the left, other people drive on the right, not so great, right? Carnage. It's going to be ugly. Let's imagine a world where we've got all these sort of 100 domains, and we've got people making idiosyncratic choices. Let's just randomly assign what people do on these. So if we send people out, they've got this incentives to coordinate with other people, sort of like the fireflies want to get in sync with people. Now remember the earlier lecture when we talked about adjusting the dials, when we talked about the coordination game, the game we considered involved greeting, whether we shake hands, kiss, or hug. Okay? Originally now, remember in that game, some of the people were shaking hands and some were bowing and others were hugging and kissing. Over time, the less common actions, say kissing, disappeared because fewer people met kissers. And eventually, if everyone keeps interacting with other people, we'd expect the whole population to coordinate on a common action, perhaps, bowing, let's say. But remember, it took a long time if we just had a network of people. This is like the fireflies. Each person is coordinating locally, and the result is emergent global coordination. The pure coordination model explains why when we visit a different country, much of what the people do seems odd or different from what we do. And what's happened is they had to coordinate with one another, and so did we, and it just randomly happened that we coordinated in different ways. So that's fine, that's cool, that's great. The problem with this simple model of thinking of the world and thinking of culture as just a collection of coordination games is it doesn't explain the fact that cultures have meaning, that they have coherence, and that it's often possible to predict how someone from a particular culture will act in a given situation. For example, all else equal, an American is more likely than someone from France to try something new and risky, right? We're much more willing to embrace uncertainty. So that's a problem. Our model of just idiosyncratic coordination won't solve that. It's too simple. So what we need to do is we need to introduce interactions between these various domains on which we're coordinating. This is in a way going to make the landscape rugged. Well, how do we do this? The way we're going to do this is we're going to assume that people value consistency. Excuse me. So if I choose to hug people when I meet them, I'm also going to be probably less formal in other settings as well. So I may put my feet up on the coffee table, or I just may touch people in casual conversation. It's maybe a looser culture. This consistency across domains allows people to figure out what to do when a new domain arises. An example helps here. So in cultures where authority gets more respect, like Malaysia, emails tend to be very formal. People in the United States have a more laid-back, equalitarian culture, and we know this because sociologists have something they call a power distance scale. The United States scores low on power distance, Malaysia scores high. As a result, I get emails from my students that say, "Hey, prof, quick question." Now, if I were in Malaysia, those same emails would say, "Dear distinguished Professor Page, I'm sorry to take up your valuable time, but," right? We see these differences. Consistency perhaps has even greater influence in belief domains. So if we have people who are very scientific in one domain, say in medical research, they believe very strongly in scientific medicine, eschewing unscientific-based approaches, right? This creates an interaction between beliefs. So people who adopt these scientific explanations in one domain are more likely to accept them in another domain. What does this mean on the ground? It means that people who believe in science-based medicine probably believe in modern astronomy. People who believe in folk medicine or mystical spirits are probably more likely to accept that maybe the sun is pulled by some chariot across the sky. So we can formalize this desire for consistency in beliefs or in actions by assuming that in addition to coordinating with other people, individuals will sometimes choose a behavior in such a way as to be consistent with themselves. So now we've got a full model, and the full model works as follows. People walk around, they meet other people, and they talk about ideas, and they see actions, and they coordinate with other people because they don't want to feel uncomfortable. At the same time, they've got interactions within their own choices. They strive for consistency. They want to avoid cognitive dissonance. So what's going to emerge from this coordination with other people and this drive for consistency? Well, what's going to emerge is something that looks a lot like culture. Broadly speaking, what we're going to get is we're going to get people that are coordinated. And broadly speaking, people are going to be consistent, some more than others. But there's going to be some variation. Just like we saw with our indigo buntings, there is no one indigo bunting. There's going to be no one French person. There's going to be variation. So if we include the possibility of errors and we instead of assume different levels of acceptance for consistent coordination, we're going to see some individuality. So cultures then can be thought of as some sort of like emergent pattern. Germans seem German, the Spanish seem Spanish, and so on. Now these cultures exhibit functionalities as well, right? So it's not just the fact that there is this notion of Frenchness. There's actually a functionality there. What is that functionality? Well, let's talk about two. First, cultures allow people to know how others will behave. Not exactly, mind you, but you have an idea. So if I go to a baseball game with someone from Japan and the home team hits a home run, I know I shouldn't hug and kiss my guest, right? Because if I know something about Japanese culture. Second, people know themselves how to behave in novel situations. So if I'm Canadian, I'm not, but let's suppose just for fun I am Canadian. If I were Canadian and I find myself in a new situation, I can just ask, what would a Canadian do? And once I know what a Canadian would do, then that's what I'll do, right? Because it gives me some comfort in terms of my actions. Okay, so we've talked about how culture is an emergent phenomenon. Now I want to talk about the emergence of a different type of functionality, which are going to be firewalls. So blinking fireflies in emergent cultures are interesting, but they're a long way from consciousness, right? To get there, we want to take some small steps. And in the next lecture, we're going to talk about a model called the game of life, and that's going to get us closer. It's not going to get us all the way there, but it's going to get us closer. For the moment, though, I want to move just sort of halfway there and talk about a particular emergent functionality, which is robustness. And I'm going to do this with a model of banks. Now, it's going to be a very simple model of banks, and it's going to work as follows. I've got a bunch of banks arranged in a line. And the idea is each bank has loans out to the neighboring banks, the banks on either side. You can think of these as callable deposits or money that it can withdraw from its two neighbors. Now, each period, each bank has a choice. It can make a safe loan or it can make a risky loan. Risky loans are going to pay $5, safe loans pay $4. So it seems like, okay, why not make the risky loan? Problem is the risky loan can go bad. Let's suppose it goes bad 10% of the time. If it goes bad 10% of the time, that means $5, maybe 10% of the time I lose the $5, the expected value is $4.50, so it's still better off to make the risky loan. Well, I want to add one more feature to my model to make it interesting, to make it complex. Let's suppose if the risky loan goes bad, that the bank doesn't just fold. What it does is it can borrow money from its two neighbors. So it can just pull its deposits from the two neighboring banks. Let's also suppose that if the neighboring bank made a safe loan, well, that's fine. You can just borrow the money and everything's cool. But if it made a risky loan, the bank's investors are going to get worried. And they're going to say, wait a minute, their risky loan failed. I want you to call our deposits from our neighbors, which will be one of the neighbors on the right. So let's assume that there's some cost to pulling these loans, pulling back these deposits from neighboring banks, and that costs like $1 or so. Well, if that's the case, then a bank would prefer to make a safe loan than to fail or to have its neighbor fail, because you've got to borrow money from the other bank. So that's the model. If you're in isolation, you'd rather make a risky loan, but because you can have these cascading failures, you'd basically like to maybe make a safe loan. So what we're going to do is we're going to start with a whole bunch of banks. Some are going to make risky loans, and some are going to make safe loans. They've all got the same problem initially, right? But they're just going to randomly make choices. Now, initially, most of the banks will probably choose to make risky loans. But then some of the banks are going to realize, uh-oh, there's too many risky loans out there, and we should avoid doing so. Now, the fact that some banks will then choose to play it safe, but others will keep taking the risk, is going to break the symmetry of the initial model. Remember we talked about breaking symmetry before? That refers to the fact that things that were once identical now differ. So the slime mold differentiated itself, so some moved up to stalk and some became spores. This concept of broken symmetry is central to emergence. So for example, the skin cells on a snake, right, on a snake's skin, they start out the same, but somehow the symmetry breaks and we get wonderful diamond-shaped patterns. Okay, so back to the banks. Enough about snakes. In our model, we've got this first period. Some of them make risky loans and some don't. Some of the banks are surrounded by other risk takers and some are surrounded by safe banks.